Okay. So the goal, obviously, the goal for the project was to build it out of off-the-shelf things as much as possible, so that it could be fairly rapidly built and cheaply built. Um, but we did have this issue where we did have to custom fabricate components with a 3D printer, um, and really only because um, we were switching. We have fluid flow, and we have valves, and we have this pressure chamber which we built ourselves. I guess I'll talk about that first. So we designed our own pressure vessel. It's this. If you look at this, look at the pictures or the images, you'll see it. It's pretty prominent. It's got like end caps and a clear plastic tube, and it supports a certain amount of volume. And it's a pressure vessel. It has to hold pressure. So we knew from the start we were going to make our own of that. And so it's, it's the kind of thing you do need a fabrication shop to do, although it's not a complex object, but you would need a machine shop to make it. It's not something you could make in a home garage, probably, unless you had those machine tools. But it is not a difficult thing from that perspective, and it's fairly simple, just a few components. So that was custom built. And then the only other custom things were fittings. And the reason for that simply was we needed to go from, and this was new on me because I wasn't familiar with this stuff. In our normal fluid flow type of thing, we would have typically pipe threaded connections perhaps, or barbed connections where we have a soft hose going on to a fitting. And so we have these pipe threads. They're tapered threads that, are certain standard sizes, and then you buy a valve or something like that and you thread that onto the pipe and you move on. That's what we had to buy for valves. Our valves had those sorts of threads, and those were in imperial sizes, by the way. And then we needed to move to medical tubing, which uses this tapered sort of approach. You see it at the hospital. These tubes just sort of mush onto each other. You just push them together, and so they use a tapered kind of thing. I have a couple of kind of preliminary 3D printed things here. Maybe I can show something. So, like, this is we've got a pipe thread here that would screw into the valve perhaps, and then over here, a hose or something else would fit right over this. This actually has a slight taper to it from here to here, 1 in 40 pitch, so that something like this could kind of just jam onto it. So these are just prototypes I printed on an FDM 3D printer, which you probably have at your school. So we had to make a bunch of these, and so I designed all these. So this, once you've got the design, it's not that difficult to print. And it can even be printed on a fairly low-cost printer. This is what we ended up using for material. You see it's gray. We've got the pipe thread here. We've got the tapered thread here. And it even got a hex thing here to put a wrench on so I can screw it together, right? Also, we have a little hole there, okay? That's where a pressure tap would go to a pressure. So all the pressure taps had to be put in somewhere, so we put them right into these custom fittings. So I'll detail this just a little because this is probably the only place you'll hear this. So how do we make this? Well, we've got a couple of choices for printers. Quinn, I assume you have FDM printers at the school?
Mm-hmm. Yep.
Right, so it squirts out the little filament of plastic and lays it in layers and builds the model, okay? That wasn't going to be acceptable for our fluid flow and our medical device, because these produce a sort of a porous object that isn't really watertight. And you can test this yourself by making a little cup or something with it and put some water in it and see where it goes. It'll eventually leak out, okay? So what we need is a printer that can make like a uniform material. So we have to use a different technology. So this technology is we have a Formlabs printer. I don't know if you have one of those or not. But they aren't that expensive, in fact, and it's the lowest cost probably for what we call SLA, or stereolithography printing, where this started out as a resin, and it was built layer by layer, just like the FDM, but a laser polymerizes the resin layer by layer and builds the object. It has no infill. Whatever is solid is solid. If you sawed it in half, if you printed a block of this and sawed it in half with a saw, it would be absolutely uniform inside. And so what we call in the engineering world, we call this an isotropic type of material. All right, so that's what I ended up printing all the parts for. Now, it's pretty tricky to make these tapered threads if you're thinking about Fusion 360 and CAD, but the truth is there's a lot of stuff out there that's kind of ready to go that somebody already did. So what I ended up doing was downloading models from McMaster-Carr, where we source a lot of components as fabricators, and they are very accurate, and they have the threads all in them, and then I just modified them. I started out with this half from the McMaster-Carr, and I built my half on this side. It was pretty easy. So there's a lot of creative ways to do this. It's not too hard. The last thing I'll mention about 3D printing something like this is, great, I modeled it perfect on the computer, and I printed it, and it wouldn't screw into the valve. And why is that? Well, it's hard to get it perfect. It shrinks, it expands. It's not exactly like when you make it on a machine. So what I did, I could have played around with that, but I was running low on time, but I have a machine shop. I ran a thing called a die over this for the pipe thread and just cleaned it up a little bit. And that's actually a pretty legit way to fix threads on a 3D printed object. So that's my discussion of 3D printed things. Hopefully that's helpful.